Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good afternoon, everyone. Today we will examine ice age cycles and the role of Milankovitch cycles in driving long-term climate change on Earth. I begin with a brief history. The term Milankovitch cycles refers to three related changes in Earth's orbit and orientation, named after Milutin Milankovitch. These are eccentricity, obliquity, and precession. Each affects how solar radiation is distributed across the planet and through the seasons. Eccentricity alters the shape of Earth's orbit from more circular to more elliptical on roughly a 100,000-year timescale. Obliquity is the tilt of the axis and varies about every 41,000 years. Precession affects the timing of the seasons relative to perihelion and changes on roughly a 23,000-year cycle. Why do these orbital changes matter for ice ages? The key is seasonal and latitudinal distribution of insolation. We often focus on summer insolation at 65 degrees north because it controls how much winter snow survives the summer melt. Low summer insolation allows snow to persist and gradually build ice sheets, while high summer insolation promotes melting and can lead to interglacial conditions. Evidence for orbital pacing of ice ages comes from marine sediment cores and ice cores. Marine foraminifera record oxygen isotope ratios that correlate with global ice volume and are used to define marine isotope stages. Ice cores from Greenland and Antarctica preserve temperature proxies and greenhouse gas concentrations that help us match orbital cycles to climate responses. A clear example is the last glacial maximum, which peaked about 21,000 years ago. That interval corresponds to orbital configurations that reduced northern summer insolation and allowed large ice sheets to expand. The subsequent deglaciation, sometimes called Termination 1, involved rising insolation, retreating ice, and an increase in atmospheric carbon dioxide by about 80 parts per million, which amplified warming. One important nuance is that orbital forcing alone is relatively small in terms of global energy, so internal feedbacks are essential. Ice-albedo feedback amplifies initial cooling as expanding ice reflects more sunlight. Changes in greenhouse gases, particularly carbon dioxide, also act as an amplifying feedback rather than the initial trigger in most cases. There is also what researchers call the 100,000-year problem. Eccentricity cycles have the correct period but weak direct radiative forcing. Many hypotheses address this issue. Some point to nonlinear responses in ice sheet dynamics, for example growth and collapse thresholds, interactions with the oceans, and modulation by precession when eccentricity increases the effectiveness of precession-driven insolation changes. Shorter-term variability is also observed. Dansgaard-Oeschger events and Heinrich events occurred within glacial periods and show that ice age climates are not smooth. These events reflect internal variability of ice sheets and ocean circulation, but they still occur against the background pacing set by orbital cycles. To reconstruct past sequences, scientists combine orbital calculations with proxy records. Orbital solutions can be computed precisely for millions of years, which provides a framework. Proxy records then reveal how ice volume, temperature, and greenhouse gases responded. For example, Marine isotope stages demonstrate the alternating glacial and interglacial states over the last few million years. Finally, understanding ice age cycles teaches us about climate sensitivity and feedbacks. While today's anthropogenic forcing differs in speed and origin from orbital forcing, studying past glacial cycles helps quantify how sensitive ice sheets and the carbon cycle are to relatively small changes in incoming solar distribution. In summary, Milankovitch cycles set the timing of ice ages by altering seasonal and regional insolation. Orbital changes interact with ice-albedo, greenhouse gas feedbacks, and ice sheet dynamics to produce the glacial and interglacial cycles recorded in sediments and ice cores.
Listen again to part of the lecture, then answer the question.
We often focus on summer insolation at 65 degrees north because it controls how much winter snow survives the summer melt.
This concludes the listening section. For more TOEFL practice tests and study materials, visit Spinta.org.